screen now. So let me see if I can share it. All right. So are you able to view the screen?
Yes, sir. Your screen is shared. Yes, sir.
Okay. Is it okay now?
Yes, sir. Can you please make it full screen, sir?
Yes, I'll do it. Huh? Is it okay?
It's perfect, sir.
Okay.
इसको height वाले को भी sir this is coming in between that height. That
Which one?
height पे click कर दीजिए sir. This stop sharing. No, near to stop sharing there is one height.
Right.
Height.
Okay. All right. Okay.
It's fully
All right.
visible. Perfect.
Okay.
Thank you, sir.
All right. Okay. Thank you. Let's now have a discussion on EV charging infrastructure. So it is mostly a discussion. I will also like to hear what your thoughts are, because EV charging infrastructure is a game that we are playing, but we don't have a proper control over it. Okay, and I have to be very honest and like open about it. The reason being that most of our EV chargers, uh, in fact, I will say 80 to 90% of our EV chargers are actually imported right now. Um, so there is a push by our government that we should make it ourselves. So many people are trying that, and many people have various degrees of success in that. But still, it is still not a complete success story. So that is what kind of makes it very interesting for all of us, because whenever there is a challenge, there is an opportunity, right? So that is the whole idea. So what we will do is that I will give you a brief introduction of why EVs came, and then we will jump to some of the fundamentals of EV charging system, like the EV chargers, and then we will see from a like infrastructure point of view, like when EV chargers are there in the grid, what happens, and in the end, I will end with my favorite topic, um, that is whether we should go for publication or go for commercialization of product, because that is one of the like uh, uh, internal fight. Internal means it is within ourselves, right? Internal fight we are having, and we have to be very clear whether we should go for publication or we should try for commercialization of our products, right? So let's start. So EVs are nothing new. So they were there for a long time. General Motors have like had electric air too, right? In 1966. Okay, back in 1966 they had EVs. Similarly, like Americans, when Americans have something, the British kind of inherently copy that. So Enfield had in 1973, around 1973, British had their own version of electric vehicle. So, but these were not very like popular. They were there. I mean, I'm pretty sure that they had a lot of. So they had various degree of success during that time, but obviously they were not very popular, right? Because if they were popular, we would have seen it. Right? So then the question is why they were not popular, right? So that's something that we will kind of cover, right? So now, before we go forward, first thing first, if you are thinking what is a EV, it doesn't. I mean, it's not very hard to think what a EV is. Like we in a normal vehicle, we put a petrol, gasoline that we will call, and the IC engine, right? IC engine, ICE will kind of move us around. The car will move around. The petrol will be kind of burnt, and then once it is depleted of petrol, we just fill our tank again, right? So basically the energy of the fuel is basically consumed, and it kind of helps us drive the vehicle. So similarly, in battery, we charge the battery, we put energy into it, and then we move around to charge. The battery get discharged, and once it gets discharged, we have to charge it back again. Okay, so this is the whole process. So it's nothing different actually. ICE engine, also it is depleting energy, and battery also it is kind of depleting energy when we move around, right? So now what is the catch here, right? So the first thing that we generally think of when we think about the EV is between petrol vehicle like IC engine and between EV, which one should I choose? So I'm giving you a small mathematical calculation of which one mathematically which one we should choose. A normal car, 20 kilometer per liter. Each liter is like 100 rupees. So you are spending about 5 rupees per kilometer, right? And for a electric vehicle, we generally have like based on the onboard charger, right? We will take about, I will say, uh, uh, like sudden amount of energy, right? Per hour we will be taking 6.6 kilowatt. So per hour the unit cost is 7 rupees, let's say 7 rupees example. Okay, so that costs about 46 rupees. Okay, and in 1 hour of charging you can put about, I will say, like that is what it's 23 miles, right? So 23 miles is 37 kilometers. So per hour of charging you can put 36 kilometer into the vehicle. So therefore per kilometer cost will be 1 rupees 25 paisa. So it is far cheaper to operate a electric vehicle. So electric vehicle is probably a clear winner when it comes to cost, right? But there are problems with that, because to charge the vehicle you require a huge amount of time. You require like a few hours in fact, right? um, but filling the tank doesn't take a lot of time. Just kind of fill the tank within minutes, right? So that is one problem. Second one is that filling, because IC engines are very common. Petrol pump, like that we call in India, are available everywhere, right? The infrastructure is well developed. But the same is not true for electric vehicle. The charging infrastructure is kind of not very well developed. It is being developed, but it is actually not very well developed. And like putting a petrol pump and putting a charging infrastructure are two different things. A charging infrastructure is a highly sophisticated instrument machine, whereas petrol pump is not a very highly sophisticated machine. It's just a pump which is kind of putting out petrol, right? Whenever we want. So if petrol pump, the pump goes bad, it is easy to replace it. But if the charger goes bad, highly skilled professionals are required to take care of it. So these are all some of the, even though monetarily EV wins, there are some roadblocks that still remain in order to make EVs more popular, right? So far you have any questions, or can I go forward? I like to kind of check, because I cannot see you, so I don't know whether I'm able to convey my point or not. So you have any questions, please let me know. Otherwise, I'll move forward. All right. Okay, so let me move forward. So if you look at inside a electric vehicle, there are many electrical components. In fact, the very name electric vehicle means that it is actually a more electrical intensive machine than a machine that has other type of things, right? Um, uh, that doesn't mean that it doesn't have mechanical engineering aspect to it, or material science aspect to it, or um, uh, AI ML aspect to it. Okay, but what I'm trying to point out is that it is like heavily dominated with electrical components, right? So that makes electric vehicle a more electrical instrument than anything else. Okay, so the opportunities are many. In fact, that is what the point is. So what happens is that we, like, if I will just make it a pointer. Okay, so there's a pointer. So now there is a plug point. Okay, so we will connect our gun, like charging gun, to this plug point. So this charging gun will charge the vehicle. So the charging will happen if I'm putting a AC input. The AC input will go to a onboard charger. The onboard charger will convert this AC into a DC, and that will go to the battery, because ultimately the battery requires a DC. Okay, it will not take a AC. So either the conversion has to be inside uh, the onboard charger, or the conversion has to be outside. So if I give a AC, then it goes through onboard charger, then the relay, and then the battery. And if I give a DC, then DC will directly go here and directly go to the bulk battery, like the EV battery, right? So and once the battery is charged, what happens is that it will see, ultimately the battery energy has to transfer to the wheel. Okay, so because wheel is the one that is rotating, right? So that happens through an inverter and a PMSM motor. So PMSM is a very common motor that EVs will use. There are other motors that are under study. So I am not an expert in motor used in EV, but we have experts in our center who actually take care of those motors. But what I was told and what I have seen from various manufacturers, Tata or Mahindra and Hyundai. So I've seen that they mostly prefer a PMSM motor, that is a permanent magnet synchronous motor, right? So, and that synchronous motor is the one that is actually controlling the wheel, but that synchronous motor has to be driven with a variable supply, right? Because we have to change the speed, right? So that happens through an inverter. Okay, so this inverter is another, the same inverter, like DC to AC inverter, right? Three phase inverter, right? So this is and then this battery is also kind of supplying. See, battery is a very funny component, because whenever the battery starts working, na, it gets hot, right? So it will get like there a lot of heat is generated, so that heat has to be kind of like cooled down, right? So that happens through a pump. So that pump is from a 12 volt, so there is also a 12 volt battery in the vehicle, right? This 12-volt battery is also supplying the electronic component of the vehicle, right? So therefore there is a DC to DC converter which is converting this bulk battery into a 12-volt. Bulk battery generally, no, it is somewhere between 250 volt and 500 volt, depending on the manufacturer, right? For example, Hyundai, they use about a 400 volt battery. So their battery voltage ranges somewhere from 300 to 500. For Tata, they mostly use a 320 volt battery. So their range is somewhere between maybe 250 to 80 to about 400, because 320, so about 400. So so similar numbers will be for Mahindra. So this bulk battery is little bit higher voltage. So why it is a little bit higher voltage? The reason is that these inverters will demand a lot of power, right? So this power, like whenever you are giving the power at a little bit higher voltage, the current will be less. So it will be kind of optimum. So the same concept that we use in power system, right? Why do we transfer power at a higher voltage, right? So that's the reason, right? Because if you transmit power at a higher voltage, then the current will be low, so I square R loss in the wires will be low. So that is actually precisely the reason why we use a little bit higher voltage battery. Okay, uh, but now this battery 300 or 400 volt battery has to be interfaced with the 12 volt, because that also needs to be charged. Okay, so that was, this 12 volt battery was always there. Actually, in our normal vehicle also it is there, in nice engine or vehicle also it is there. So the additional task the 12 volt battery has, apart from supplying all the electronic components in the vehicle, is the battery cooling pump. That is the extra work that it has to kind of do in an electric vehicle. But I mean, from internet I have got the numbers. Okay, so these are some of the numbers that I actually got. So onboard charger is somewhere between 200 to 450 volt. It is depending on the manufacturer, this kilowatt rating will change. Normally it is the maximum is 7.2 kilowatt, that in India people will kind of use. If in many of Tata vehicle they have 7.2 kilowatt, even Hyundai has 7.2 kilowatt kind of a rating for onboard charger. And these are some of the numbers that I have kind of figured out. And then relay, then bulk battery. 30 kilowatt hour is a standard bulk battery people will use, about 320 volt, but it can be a little bit higher also, because I, like I told you, in Hyundai it is like 400 volt or so. Okay, so different car manufacturers use different type of voltages depending on their design, right? And PMSM is, you can see that it is a very good PMSM, high power PMSM, about 80 kilowatt or so, and that is the efficiency and voltage numbers for it. And inverters, similarly, you can get the voltage numbers here. All right. And like the DC to DC converter, that is this converter that is interfacing between the 12 volt and the bulk battery. This is some of the numbers I got from the internet, and similarly the other things also you can see. All right. So now the question now, like, let me come back to the original question. See, this gives you an overview. So while doing this, uh, I asked a question, that why it did not become successful. That was one of the conclusions I made, and then I was telling you that I will discuss about those conclusions at a later part. So now let's discuss the conclusion. Why in 1966 the electric vehicle that came, the GM came with, General Motors came with, it did not become successful. So there are fundamentally two technologies that have improved over the last 40 50 years, right? So the first one is the battery technology. Lithium ion battery has become prominent, and power electronic technology. Power electronic technology, in power electronics, now switches are far better. Okay, so that makes power electronics far more viable in case of electric vehicles. See, the whole idea is that if we have a very small battery that packs a lot of energy, that is a good thing for us, right? So just check, just 1 minute, just 1 minute. Stop there. So if I have a small battery that packs a lot of energy, then that is actually a good thing for me. So that has happened now. In a very small lightweight battery has a lot of energy in lithium ion battery. And similarly, power electronic technology, if I have to, you can see here that there are a lot of power electronic converter involved, like onboard charger, inverter, DC to DC converter. So previously the technology was not available to make these compact. Okay, because the switches were of low rating, the voltage rating was not good enough. So now all these problems have been kind of solved. Okay, and now the with present technology we can actually make a power electronic converter in a very like the power density can be made very good, right? So what that does is that it results in a very lightweight power converter which can be put into an electric vehicle. Because if the electric vehicle is carrying a very big power electronic converter, it has to basically, it's not efficient, right? So that is something that has happened. So let me elaborate it a little bit. So what has happened is that in 1966 people were using lead acid battery. Okay. So lead acid battery has various disadvantages compared to a lithium ion battery. So one is the energy density. So energy density means the nominal voltage times the rated battery capacity. So that is the energy density of the battery. So energy density of a lithium ion battery is far higher compared to a lead acid battery. Okay, so then another good thing that has happened with lithium ion is the depth of discharge. Depth of discharge means the lithium ion battery can be discharged to 0%, and then it comes back to life when you charge it. You can think of your cell phone. It goes to 0%, and then when you charge it, it again comes back to life, and this can happen uh, more often. Like many times it can do that. Like every day we do that with our cell phone, right? We discharge it completely and then charge it back again. Still the battery will last for 3 4 years, 2 3 years maybe, right? The same is not true for lead acid battery. The depth of discharge, if you discharge the lead acid battery to a very low SOC, that state of charge, then charging back again, it will do, but then it cannot do many times. Actually, depth of discharge is not that good for a lead acid battery, and going for a higher depth of discharge, that means discharging a lead acid battery to a very low voltage, actually doesn't bring it, that doesn't make its life. Like doesn't increase its life life of the battery, right? That's why as far as depth of discharge is concerned, lithium ion battery has a excellent depth of discharge, and it can do that many times over its lifetime. Okay. And the one of the another important thing, durability, long life, that's fine, but another one of the very important thing that has happened with a lithium ion battery is that it has excellent charging time. The reason is that you can actually charge a lithium ion battery at 2C or 3C. That means much higher capacity than its own capacity. Like if a 100 the 30 kilowatt hour battery is there, if I charge it at 30 kilowatt, I'm charging at C, right? Capacity of the battery, C rate of the battery. I can also charge it at 60 kilowatt, which is 2C, or 90 kilowatt, that is 3C. Okay, and by doing that I am actually reducing the charging time. If I charge a 30 kilowatt battery at C, okay, that means I'm charging a 30 kilowatt battery at 30 kilowatt. Okay, so then I will take 1 hour to completely charge the battery. If I'm charging a 30 kilowatt battery at 2C, then I'm charging at 60 kilowatt. So then the timing of my charging will be half an hour, because I'm a 30 kilowatt battery, 30 kilowatt into 1 hour, 30 kilowatt hour battery, I'm charging at 60 kilowatt. That means I will take half the time, like half an hour, right? And if I charge it at 3C, then I will take 20 minutes, because C, if I charge it at C, it will take 1 hour. If I charge it at 3C, it will take 1 by 3 hour. 1 by 3 hour is about 20 minutes. So, but the battery should allow to do that, right? In lead acid, the lead acid battery doesn't allow you to charge it at more than C, actually. In fact, as far as my experience goes, it can maximum charge at zero point 0.6 or zero point 0.7 C. It cannot charge more than that. Okay, at a capacity more than that. So that makes lithium ion battery extremely viable as far as electric vehicle is concerned, because when you are stuck on the highway, your main concern is that charge the vehicle very fast and then get out of there, right? So this can only happen in lithium ion battery. So these are some of the examples of why lithium ion battery have become very popular nowadays, and they and why uh, EV has become a viable option for us, right? Here I am not discussing about the political factors like lithium ion, whether it is available in India or not. That I am not saying. I'm not discussing that. I'm only discussing the technical part of it, right? So now, if you think about a power electronic converter, so you can see that 1957 people used to use SCR. So SCR was a big change over a diode. A diode, the turn on cannot be controlled, turn off also cannot be controlled, depending on the voltage across around it, a sine wave or whatever voltage around it, it will turn on automatically and turn off automatically. So in SCR, they said that okay, at least the turn on part we can take care. So they were able to turn it on, but turn off they could not do. They cannot turn it off. So turn off will be happening like based on the circuit condition, right? And then BJTs, GTOs, gate turn off thyristor. So all these things actually came because they wanted to have control over that turn on as well as turn off. So now slowly what has happened is in 1976 MOSFET came. Okay, MOSFET came, and then IGBTs came. Then not like modern system, a lot of wide bandgap devices have come. Wide bandgap devices means silicon carbide MOSFET or GaN MOSFET, etc. have come. So you can see that over a period of 50, 60 years, what has happened is that a CR, which was a bigger device, has been replaced with a extremely small device which has a voltage rating of 650 volt and a huge current rating. So what that means is that whenever you use this wide bandgap devices to realize your power converter, it is actually very compact. The power density becomes very good. Okay, in this system. So I will just take a pause here, uh, if there are any questions so far, I can take it up. If there are no questions, I will go forward. Uh, uh, is there any questions so far? The material that we have covered.
Uh, Good afternoon, sir.
Yes, yes, please, sir.
Sir, I need to ask one question.
Mhm.
That is there any, sir, global standardization for bulk batteries in EV charging? EV.
People generally use lithium ion battery. That is the standardization. Because what they have see the problem with the reason for this standardization is that they want a lot of safety. Okay, and because lithium ion battery is used in like by almost all manufacturers, so the safety aspect of that lithium ion battery has been very but at least the superiority of research done to for the safety of those lithium ion batteries far greater compared to other type of batteries. So the question, if the question is what type of batteries people use, standardization means that, right? So then
But I
lithium
think
ion battery is the one.
it's about voltage rating of standardization
Yes,
about
sir.
voltage rating of the
Oh,
battery.
even the voltage rating. Okay, so voltage rating. So generally, what happens is that okay, so voltage rating is very much related to the power rating, right? So if there is in a 30 to 40 kilowatt energy density kilowatt hour battery, okay, normally the voltage ranges from 200 volt, like I was telling here, na? So the voltage rating of the voltage will be 200 volt to 450. But this is the battery rating actually, okay, because that is what the battery is charged with, right? So 200 to 450 volt. Okay, so that is in India, whatever vehicles are sold now at this voltage level. But now Mercedes has come up with systems where the battery is no longer 30 kilowatt hour. It is far higher than that, like 60 kilowatt hour. In fact, MG has also come up with a 60 kilowatt hour, and there are other manufacturers which are following suit. So whenever you are going up in the rating of the battery, the voltage invariably will go up. The reason being that the requirement of current will otherwise be very high. So unless you go up in voltage, see, current is equal to power divided by the voltage, right? So you have to go up with the voltage in order to reduce the current so that there is less I square R loss. So like normally in India, it is somewhere between, I wouldn't say 200 even, it is somewhere around 250 to 450. Okay. And current scenario, the most common scenario. But for higher capacity battery, the voltage has gone up to about 650 volt or so. Right now, like Mercedes, etc., have uh, uh, cars which are about 650 volt or so. Does that answer the question? Did I confuse you? Did I answer your question?
Yes, sir.
Okay. All right. Is
So
there
I
any?
think, sir, this is due to different watt power ratings, that voltage rating is not particularly standardized to certain voltages. Right?
It's the battery voltage is actually driving what voltage to use for the battery. If the battery rating is higher, the voltage will be higher.
Like otherwise, it could be multiple of integer multiple of 48 or 12, something like that. That
No,
way it could be done.
it's like standard, like 320, 450, 650, like that the numbers are there.
Okay.
Right.
Okay. Okay, sir. Thank you. Please continue. Thank you, sir.
Okay. Any other questions or can I continue?
Sir, one more question.
Hmm. Yes, sir, please.
Sir, actually, it is a type of case study type question. One of my relative was traveling from Delhi to Jaipur, and at the initial time, the EV was showing that it is 100% charged.
Hmm.
So it should easily come to Jaipur. But in the midway, the battery was dead, and the vehicle was was stopped in the midway. So how to mitigate this issue?
See, this generally doesn't happen. I think there is some issue with the battery. Okay. I'm
Okay.
not a battery expert, by the way, but what you are basically saying is that, like you can see your cell phone, right? There's a continual decrease in its capacity, right? So it
Yes, sir.
doesn't happen that up to 50% it takes and then 52. It doesn't. I don't think it has happened with my cell phone at least. So lithium and the car is no different, right? This is also a lithium ion battery. So I will, uh, I mean, if I have to guess, it has to do something with the way it was kind of used. That is one problem can be there. Or second one is that there may be some problem with the battery itself. Okay, because this is not something that is. I mean, think about your cell phone. Now that will give you an idea what has happened, right?
Yes, sir. Yes, sir. Thank you, sir.
Uh-huh. So, okay. So, any other question, or can we go forward? Okay. So let's go forward. So now, so I kept on telling you that there is a continual in change in the power switches. So now what I will do is that I will kind of come to 2026 and tell you how the power switches are being used in various applications. Okay. So when you ask a person like me about power electronics, okay, so we actually teach or deal with power electronics very differently from what was traditionally done in your undergraduate, right? In your undergraduate, what you guys must have done is that there was a lot of effort in your power electronic course done to teach you about the choppers, rectifiers, inverters, etc. For a person like me, or for a modern designer, I will say, if that is what will satisfy you. Then for us, actually, inverters, rectifiers, DC to DC converter, nothing is different. For us, wattage is the one that is very important for us, because no matter whether it is an inverter, rectifier, or DC to DC converter, at the end of the day, the MOSFET is actually switching a voltage or a current. Okay, so we have to kind of decide the MOSFET rating, or the switch rating based on the voltage or the current that it is switching. So from that point of view, if you look at the mapping here, normally at very high power. Okay, very high power. So something like very high power will be examples of solar farm, yeah, HVDC station, something like that. So they will use line commutation or maximum an IGBT. Okay, that too at a very low frequency of 1 kilohertz or something. All right. So at megawatt level, they will kind of use that, and the switching frequency will be lower than actually 1 kilohertz. Okay. But then there are um, like UPSs, like hundreds of kilowatt or solar PV plant. So there people will use IGBT and SIC. They are very common nowadays. So previously, like 10 years, 10 years back, IGBT was more common. But with time, what has happened is that SIC has become very cheap. Okay. In fact, most of our modern design that I work on with industry, I actually prefer a SIC compared to a IGBT, because cost wise they are pretty similar. And SIC has the advantage that I can actually switch it at a much higher frequency. What that does is that reduces the magnetic size. So the major advantage of switching at a higher frequency is that your magnetic size can be reduced. The inductor and transformer size can be reduced because a smaller core is basically required, because the frequency is much higher now, right? So that is the thing. Then the next will be like rooftop PV, which is at 3 kilowatt, 5 kilowatt, 10 kilowatt, something like that. So there hundreds of kilohertz MOSFETs are generally being used. Like all, like if you buy a rooftop solar, you are more likely to have a design with MOSFET or IGBT. Okay. Silicon carbide MOSFETs are also kind of common in this application. So wherever you see IGBT, their silicon carbide MOSFETs have become important. All right. And then at smaller power, that means our cell phones and smaller power, right? So there is called consumer electronics. So consumer electronics GaN devices are very common. So that is why if you go to Texas Instrument website, okay, so Texas Instrument makes IC, right? That is what they make. But if you see, na, they will make a lot of GaN MOSFETs, etc. Why is Texas Instrument making GaN MOSFET? The reason is that actually they use a lot of GaN MOSFET. So whenever they use a lot of GaN MOSFET, all these big companies have this way of doing things, that if they're using a lot, why not make it yourself, so that you can the controller also can be integrated into it. So GaN devices, at a very low power level, GaN devices have become very common. But see, here I will give you a small detour, that some of the designs which are, let's say, rooftop solar or something like that. So where uh, cost is not an issue. Okay, let's say I am making a solar uh, plant, solar power converter for a satellite. Okay, whenever I'm making it for a satellite, I don't have to make it cheap. But whenever I'm making it for a satellite, I have to make it very reliable, because once it leaves Earth, it is in the space. There cannot be any failure in the system, right? So therefore, whenever you do things at a satellite level, which are of very high reliability stuff, and their weight is a problem, like it has to be very light. So there, many of the designs, like where weight is a problem and reliability is an issue, there people tend to use GaN MOSFET as well. So you will see GaN MOSFET in other designs as well, depending on the application. So if the application is for selling it to the general public, rooftop solar, no one cares about GaN MOSFET, because the cost will be too high. No one will buy it. Okay. But whenever we are doing it for a satellite, the weight is important. Cost is never an issue when you are sending it to satellite, because millions of rupees are spent, and a power converter, like just because it's 10 rupees cheaper, no one will be using your power converter. So there people will use a GaN device kind of a thing. All right. So now, depending on this, also the switching frequency will vary. So when you have a very high power, the switching frequency will be very low. But when you go for a RF type of amplifier, that is there's a consumer electronics amplifier, the switching frequency will be extremely high, because their portability is very important. So, and portability comes from two things. One is if you can reduce the loss in the switches, then the second one is if you can reduce the magnetic size, because magnetics and the heat sink of a switch, okay, they are the one that takes the maximum space. All right. So therefore, if you can reduce the magnetic size and make the switches cooler, then that will make like that will actually make it portable. So that kind of happens in very high frequency design. But very high frequency design do not give a lot of power. It will be very 1 watt. So one very interesting thing you will see is that a solar farm, let's say, okay, solar farm is giving out a huge amount of power, like 1 megawatt of power. So if you say that I made a solar farm, the solar farm inverter which has 99% efficiency, so that means 1% loss is there. So 1% loss, give or take a thumb rule, 1% loss of 1 megawatt is how much? One is about 10 kilowatt or so. So 10 kilowatt is still a very high power, right? So that the 10 kilowatt of heat is generated. So a 99% efficient 1 megawatt power plant is not a good power plant. A 1 megawatt power plant should have 99.99% efficiency. But think about a 1 watt converter. So if I say that I have a 99% efficient 1 watt converter, no one cares. Why? Because 1 watt is the output power. So 1% of that is a very small number. So why you need to have that smaller number if the cost is very high? If cost like is not high, people will agree to you. But if you say that I have a 50% efficient 1 watt converter, but it is half the price of 99% efficient converter, then people will be agreeing to it, right? People will say that अरे वो कितना पैसा क्यों खर्च करना है, because 1 watt 50% is 0.5 watt. 0.5 watt loss doesn't matter to us, okay? But if the cost is low, it doesn't matter to us. But you will say that no, I want to make it 99% efficient, but the cost will be 3 times. Then no one will worry about it, because the guy who is selling it for cheap, he will always win the battle. So these are the mapping of how power switches are used in what type of a converter. And one thing you must have seen here is that we don't make distinction between an inverter, a DC to DC converter, or a or a rectifier, like in traditional power electronic courses people do. So for us, they are all the same. It is the technology that you use in these systems that is more important. Okay. So now
Sir,
come. Yes.
I have one. Normally, this SIC and GAIN device, they are placed together, calling them to be modern devices. But in this slide, like SIC is placed at low frequency device before MOSFETs. In fact,
Oh no, that is the wattage, based on wattage rating. I'm kind of telling you. Let me just draw a map for you. I'm just trying to search. So just give me 1 second. I'll see the issue here is that this mapping is not based on. It is based on the wattage rating. Okay. Okay, the mapping goes like this. That see MOSFET, silicon MOSFET. Let me just turn this one on so that I can write on top of this. You know? So if you think about a silicon MOSFET, like if I just go back. All right. So if you like, what happens is that the silicon MOSFET, silicon FET. So normally the silicon FETs are available from somewhere around, let's say, 1 volt to 650 volt. Okay, best of the silicon MOSFETs are available in this voltage range. Okay, then IGBTs, they start from 650 volt to somewhere around, let's say, 2300 or even higher, actually, even higher than that. Then the silicon carbide MOSFET, they are also of the same rating. Okay, so therefore you can see that whenever I am saying IGBT, I am also saying that silicon carbide, because it depends. Like older design will use like IGBT, but modern design will use silicon carbide. Okay. Now this GaN MOSFET, GaN, gallium nitride MOSFET, they are also from that 1 volt. They're not even 1 volt. It's like 100 volt to 650 volt. That is where they are available. So, because I was kind of there when these things were being invented, so the way the mapping was actually done was, they made GaN MOSFET, GaN, to replace silicon MOSFET. Okay. And they made silicon carbide MOSFET to replace IGBT, because you can see that that is the voltage at which it is working. So does that answer your question, or?
Yes, yes. So frequency wise, SiC is on higher side to MOSFETs, right? Si MOSFETs.
Uh, no. See, frequency. Come again.
Operating frequency, like SiC devices are having more switching frequency than Si MOSFETs.
No. They are having more frequency than IGBT. IGBT is maximum 20 kilohertz. This one can go to 100 kilohertz. Silicon MOSFET are maximum 500, like modern design 500 kilohertz, 1 megahertz. GaN MOSFET 1 megahertz onwards you can have advantage. Okay, so that is the rate.
Thank you.
So see, wherever you previously you were using IGBT, you can think of replacing with silicon carbide MOSFET, because they will have available in same footprint. Okay, and you can just put it there, the same driver will drive it, but you can have higher switching frequency so that the magnetic size will reduce. So that magnetic size I will just go through now.
Yes, sir. Thank you, sir.
Okay, so the magnetic size wise, if you think about it, then let me just make it pointer. I'll just make. So magnetic size, if you think about it, so normally in 50 hertz, at 50 hertz we'll use CRGO, like iron core, right? And then little bit higher frequency we go for amorphous core, and nanocrystalline core. Actually they are very modern designs in high, like 800 or 500 kilowatt charger. They are very very popular. Then ferrite core, they are normal ferrite core that like at hundreds of kilohertz they will be popular, and then nickel manganese at megahertz level they will be kind of popular, right? So this is the mapping of your cores, right? So now the question is that I like one of the questions that I used to have when I studied this was that why can a iron core be used in megahertz range? Okay, that was one of the questions I had. So that actually has to do with the resistivity. So this resistivity numbers, if you see, then you will actually understand why people use ferrite core at high frequency and CRGO core at lower frequency. So what is resistivity? Resistivity means that the core is also a conducting material, right? So when you are having wires wrapped around it and having magnetic field, so that magnetic field is it is in putting inducing voltage in the secondary, as well as it is inducing voltage in the core itself, right? So if it is inducing in the core itself, then there is a current because of that. So that is called eddy current. Okay, so this resistivity leads to eddy current. So you can see that in a CRGO core at 50 hertz, this is the resistivity. Think about eddy current and its frequency relation. So eddy current is directly proportional to the eddy current loss is directly proportional to the square of the frequency. So if I operate a 50 hertz transformer at 100 hertz, my eddy current loss has become 4 times now. So if I am doing it at 100 kilohertz, then you can imagine what is the amount of eddy current loss that will kind of happen. So therefore, people will use a ferrite core which has a higher resistivity, much higher. That means like ferrite core doesn't even have any circulating current, eddy current, right? Because of this type of resistivity, right? And that is why it is like it is better to use a ferrite core when you, and the point is that at very high frequency operation you don't require a lot of inductance. The inductance size etc. are actually far reduced, right? So therefore you can get away with a ferrite core which is much lighter than a CRGO core, right? So that is the trick here. So this is these are the pictures. But normally, like whenever they initially they come up with this nano crystalline core in, I think, 2010 or 11, they came up with this. So I bought some nano crystalline core from, I imported it from Taiwan. I was at IIT Kanpur back then. So so what happened was that the nano crystalline core was a structure. It is not, there was no like lamination there. See, in a normal CRGO core we use lamination. Why do we use lamination? Because we want to reduce the eddy current. Okay, because this resistivity is pretty high. In order to increase the resistance, we want to rho L over A, right? So we want to increase the value of A, right? Area, right? So that sorry, decrease the value of area so that the resistance is kind of high, so that no eddy current will flow, right? So that is why we kind of laminate the core. So this lamination was not there in nanocrystalline core, and the reason was that they were generally using nanocrystalline core for transformers back then. So in transformer there is no residual, a very little residual magnetic field, right? Because the primary field and the secondary field cancel each other. So there is, but when we try to use it as an inductor, we always used faced a lot of problem. And when my students used to say that, sir, this is heating up, I said, how can it heat up? It's a nanocrystalline core, it's supposed to be good. So then I realized that it doesn't have any lamination. So, but modern systems, they figured it out that like people will also use for inductance, right? In rather than transformer, they can also use it for an inductor. So now they provide this nanocrystalline core with laminations. Okay, so you can actually like if you are planning to make a, let's say, 500 kilowatt charger or something, so this is the one that you will be using. Actually, they are only available in C core format. There is no E core. So basically, in order to make it a E core, they use, for a C core you will use two cores, right? So for a E core you have to use four cores. That means one core you can put here and another here. So that becomes a E core kind of a thing for you. So that is what things have happened. And for low power, like low power application in our consumer electronic systems, people will use a ferrite core, either manganese zinc if it is in hundreds of kilohertz, and if it is in megahertz range they will use nickel zinc, because nickel zinc has a far higher resistivity compared to manganese zinc. Okay, so this is a, like I figured out that this is a excellent material science research. Okay, and they get into problem and they do a lot of material science research, especially in Japan. They do this kind of things. They have many material science related labs there, so they do that. I was kind of fascinated with how they conduct their research and come up with new thing in front of our eyes. They come up with new things, right? So it is not like they were sitting idle. They are actually doing research and coming up with new stuff, and similar to us, right? In many fields we are also coming up with new stuff. But anyway, so that any
Sir,
questions?
in this ferrite last one, nickel zinc, like permeability is very low. So for having inductance is proportional to permeability. But I think this resistivity part will cover that. Is
No,
it so?
see, so the trick here is that you don't require a lot of inductance in these fields, in these
Okay.
systems, right? Because it is like very lightweight, right? So it is operating at
Inductance is very
megahertz,
high. Yeah,
megahertz,
very
na?
high.
So inductance will be very
Very
low.
few turns are sufficient
Few
to
turns
induct.
are sufficient. Yes, yes.
Okay, fine.
Okay, so various types of electric vehicle are there. I mean, I am not an expert in this. This slide is there for completeness. Okay, so battery electric vehicle is what we are talking about. Only battery is the one that kind of drives the car. But there are also cars like plug-in electric, where gasoline or electricity from the grid can be used as a fuel. So both are able to drive the system. And then there is something called a hybrid electric vehicle, which is a smart hybrid and things like that. So there what happens is that the battery is only responsible for the electronic component. So it is a primarily works on gasoline, but battery is basically used for the electronic component. So that way the battery usage, right, the mileage of the gasoline actually improves. Actually, I have also seen that. I have a hybrid electric vehicle, and many of you must be having. I have S Cross, right? S Cross is a smart hybrid, they call it. It has it has very good fuel range compared to a like a only gasoline type of vehicle which I used to have before, right? So these are some of the types of EVs that are there. But now one of my question was, this is a very interesting slide. Question was that uh, how come uh, like uh, to charge a battery requires so much time? Why does it require so much time to charge a battery? Uh, why can't it be done even faster than that? So this slide will give you the answer to that. Why? Like this is one of the question, right? You must be having it. Why does it require to charge so much time to charge a battery? So the reason is actually this. So this is, if you know the difference between these two scenario, then you will know why it takes less time to fill and why battery takes more time to charge. Okay, so what happens is that the story goes like this. So if you think about it, in a 3 month period people can come up with a huge building. Okay, so huge building means a 50 feet it will go up. Okay, but if you think about like my daughter or our kids, they take about 13 years to go from a kid to whatever growth they have had now. So why our kids growth is much slower, and why we can grow a building with of 50 meter in a 3 month period? The reason being that when you are thinking about a building, actually many people are eating food. They are they digest that food, and that is converted to energy. And many people like that are putting all that energy into this like construction. Okay, and that's why this actually takes a less time to kind of grow. But however, the growth of our child is a chemical process. Like you eat, it takes some time to digest, then slowly they grow, right? So that is the difference. So this, if you know these two difference, you will know the difference between gasoline. So mother earth has taken uh, thousands of years to make this petrol, right, make this gasoline. And what we are doing is that we are just taking it and dumping it and kind of blowing it out on our vehicle. However, in a battery is more a chemical process. So when you are charging a battery, you are not dumping any energy there. You are actually, it is a chemical process. So that why it takes a certain amount of time to charge. So if you understand this, you will also understand that doing a 2C 3C charging to the battery will ultimately make its life lower, because it is like having steroid and growing, right? So you cannot sustain that process, right? It cannot go on forever, right? So natural process, if you follow, then it takes a lot of time. So that is why when you talk to battery manufacturers or people, if you have a EV, they will talk talk to you about charging the TV. You will always hear them saying that try to charge it at night, which like 7 hours, because slowly it will charge. Don't do a lot of fast charging, because that is like not a good thing for the battery or its long term health of a battery. So this kind of, I thought that this analogy was very important for me, for my brain to wrap around the fact that why battery takes a lot of time to charge, and why gasoline's like just kind of 2 minutes we can fill it up and use it, right? So hopefully it was clear. Now if you like, if I go back to my original picture and I was asking you this question there, that like what does this 2 volt 12-volt battery do, and I told you that this 12-volt battery was always there. It never went away. Okay, the reason actually it is there is, the slide is here now. So what we had, see, this 12-volt battery does a lot of electronic control of our system. So seat adjustment, mirror, power steering, all kinds of electronic infotainment system, we play music, etc. That actually comes from the 12-volt battery. And 320-volt battery, the high power battery, that is actually only responsible for the drivetrain part of it, right? So what this EV manufacturers did was, they never took away this 12-volt battery. The reason being that when you enter into a EV, they don't want you to feel any different from a normal vehicle. So therefore, they kept that concept, that feel intact, so that whenever you enter into electric vehicle, you will feel that you are entering a normal car. Okay, but the only thing that changes there is the propulsion system. There was a IC engine for propulsion. Now there is a electrical drive train for propulsion. Okay, so that is one of the things that you will kind of see in any electric vehicle or any IC engine vehicle. So this 12-volt battery bus will be constant. It has not changed. All right. So now if you want to think about the charger, okay, so charger, there are two types of charger that are there. So one is a AC charger. So we have a AC voltage, AC power, and the AC power is taken by an onboard charger, which converts it into a DC. Okay. Um, so I have to say AC to DC here. So it converts it to a DC and then gives power to the battery pack. So but the onboard charger is inside the vehicle, therefore it can have only limited capacity. So it is 3 to 7 kilowatt. It is not 6, it's 7 kilowatt. So now for a DC fast charger, so there what is happening is that the power is converted directly into the DC, and the battery is charged. So because it is directly converted, so therefore the charger can be outside the vehicle, because you can have a higher rating charger. Okay, so that's why you will see all the fast chargers are actually outside the vehicle, and the AC charger is a slow charger that is inside the vehicle. That is basically given that, even though you don't have fast charger, you just take from the grid supply that is available and charge your vehicle. But it will take a longer time because it is a smaller wattage rating, and the fast charger will take a very less time, because the charger itself, the power that the charger can give is pretty high, right? So and then there are 4 types of converters. If you want to take a look at the power electronic part of it, even though I told you that we don't care about charger or converter, what they do, but actually there are 4 types of converter. There is a DC to DC converter, AC to AC converter, AC to DC, and DC to AC. So this AC to AC converter is not very common nowadays. It was very common before, not anymore. This is that cyclo converter we used to read, right? So this is not no longer used as such. Okay, so how they are used? No, now what they do is that they actually couple a rectifier and an inverter to make AC to AC converter. So you can see that a rectifier is a AC to DC, and if I put a DC to AC here, then I will get AC to AC converter. Okay, and some of the examples of that AC to AC converter is like your let's say washing machine. So see, washing machine, ultimately you are driving a motor, which is a like a induction motor, right? So and this motor, like you have variable frequency drive, right? So therefore, the frequency of the output has to be controlled. So, but the input frequency is 50 hertz. So what they do is that they actually have a rectifier, and then a rectifier supplies an inverter, and the inverter output is given to the motor, right? It's very common in modern systems. So people don't use AC to AC converter, they basically couple a rectifier and an inverter, right? So whenever you look at a converter, the converter has two parts. One is a power stage, another is a control stage. The power stage is the one that kind of takes power from the input and transfers it to the output. But how the transfer will take place, means in which form the transfer will take place, is taken care by the control system. Like for example, let's say your input voltage is 230 volt, but I want a current which is like charging my laptop. So my laptop output voltage is like or no, the charger output voltage of my laptop is 19 volt, because your laptop has a 19 volt battery. So now like a 230 volt, the output has to be 19. So this, who will decide it is 19 or not? That will, a control system will take care that this 19 volt is kind of supplied to the laptop battery at the current it expects to. Let's say the current is 5 amp, 10 amp, then that the control system will make sure that the 5 amp is flowing. It will not be 20 amp or 30 amp. Like whenever you are saying that only transfer 5 amp of output power to the battery, then the controller will make sure that that kind of happens. So I will pause here and again ask you, what if there are any questions, I can take it up. Otherwise you will sleep, I know, because I cannot see you. I am pretty sure you will sleep. Any questions? Any questions anywhere here? Nothing? Okay. All right. One, hopefully I'm audible, right? Hello? Manmohan, am I audible? Okay, okay, all right. Okay, I thought that I lost you, all of you. Anyway, so let's go forward then. Okay, so now let's go to the next one. Okay, so now like this converter, like whenever we look at a converter and it is charging a battery, any converter and any battery, you can think of your cell phone, you can think of your laptop, you can think of your tablet, or you can think of your EV. They're all same, only the power rating is different. So whenever we charge our cell phone, you must have seen that there is a something called ultra fast charger. What does that do? Actually what it is doing is that it is actually charging uh, the battery at a very high current. All right, so that is why it is called ultra fast charger. But now who will decide that current? So that is decided by the battery manufacturer. So battery manufacturer will tell you that at this current if you charge the battery it is safe, and this is the maximum current at which you can charge. So that maximum current you can actually put. So now said that, you are actually in a trouble. The reason is that whenever you are saying that I have to charge the battery with a current, that means the power stage has to act like a current source. Okay, so normally we are very used to voltage sources, we are not used to current sources. Now this power converter or the charger that you are having, this is charging the battery with a current. It is the same charger is charging the battery with a voltage, CCCV charging, right? So this is the CCCV charging. So what happens is that when the battery SOC is low, the state of charge is low, then the charger actually becomes a current source. Okay, and when the battery SOC becomes high, the charger becomes a voltage source. That means the same charger, it is a current source when the battery SOC is low, and it is a voltage source when the battery SOC is high. So that means the same charger, it has to work like a current source. The same charger also has to work like a voltage source. And based on what they will be converting from current source to voltage source, based on the SOC of the charging. So when the SOC is low, it has to be a current source. When the SOC is high, it has to be a voltage source. Now you might be thinking, how do I know what the SOC is? Actually, SOC has a direct dependence on the terminal voltage of the battery. If the terminal voltage, like for a 12-volt battery, let's think, a 12-volt battery, when it is fully discharged, the voltage will be about 11.3 or 11.4 volt. Okay, and as you charge the battery, okay, it will go up, but until 14.1, it will reach about 80% SOC, and then 14.1 to 14.4, it will reach 100% SOC. So what that means is, depending on the SOC, the terminal voltage is actually changing. Low SOC, low terminal voltage; high SOC, high terminal voltage. So we use that terminal voltage to convert the converter into a current source or a voltage source, right? So this is how a CCCV charging kind of works. So now, how does that happen? Actually, if you remember your control system, so if you like, there's a feedback system, right? If I take the output voltage as my feedback and regulate the converter, then my output voltage, the voltage here, will be fixed at the reference voltage. So what that will do is that will convert the converter into a voltage source. The reason is that the voltage at the output terminal is not dependent on the load. Load may be 1 ohm or 10 ohm. Like, as long as the converter is able to supply that, the output voltage will be fixed at Vref. So therefore, it will become a voltage source. So similarly, if I, instead of output voltage, if I give the inductor current, why am I giving output voltage? It is a capacitor voltage, it's a state variable, right? So similarly, inductor current is another state variable. So if I give that as a feedback, then what will happen is that the current through the charger will be kind of fixed, right? So that is the thing. So if I take the output voltage as my feedback, the voltage remains fixed. If I take current, inductor current as my feedback, the output current will be fixed. So therefore, in this case, it has become a current source. The converter has become a current source, and in this case, the converter has become a voltage source. So that is how the same converter works like a current source as well as a voltage source, because that is what we had to do, right? We have to make the converter work like a current source and work like a voltage source. So this is how it actually happens, right? So now let's go to the power stage. So like, I have given a simple example of a buck converter. No one uses a buck converter for charging electric vehicle systems. So if you look at a charger, it is actually a two-stage charger. So the first stage is a rectifier, okay, and the second stage is a DC to DC converter, okay. So now the rectifier actually converts AC to DC. The rectifier is also responsible to take care of the grid codes. Grid code means the TSD, the harmonic requirements, all these things. The stage one, the input stage, has to take care, right? Um, the second stage is there to provide isolation, because like, whenever you have a grid, it is a AC voltage. So like a battery, like the EV is a DC system, so there has to be galvanic isolation, transformer isolation between them. So that is provided by stage 2. Okay. So therefore, the stage 2 is actually a DC to DC converter, which will provide you the galvanic isolation. So you might be thinking that why can't we have only stage 1 and directly charge the battery? So the reason you do not do that is because the stage 1, we basically divide the functionality. The stage 1 is taking care of the grid, the stage 2 is taking care of the electric vehicle, because when you charge an electric vehicle, it is not like a straightforward process. Okay, so when you charge an electric vehicle, there is a communication between electric vehicle and the charger, and based on that, the power transfer takes place. So that is taken care by this stage 2. So as far as converters are concerned, I will not go into the details of the converter, because that will actually bore you. But what I am mapping here is that in a single phase charger means this is a single phase charger. This onboard charger will be a single phase charger. This will be a three phase charger. The reason it is three phase is that the wattage rating will be more than 7 kilowatt. And why it is single phase? Because the wattage rating is somewhere between 3 to 7 kilowatt. So 3 to 7 kilowatt. Why are we using single phase? Because as per our norms in our power system, in our power that is provided to us, utility grid, 32 amperes is the maximum current we can draw from a plug, right? So 32 times 230 will be about 7 kilowatt. That is where the number comes from. But mostly if you use a 15 ampere plug, naturally you cannot charge the vehicle at 7 kilowatt. So if you use a 15 ampere plug, your charging power will be 15 ampere times 230. Okay, assuming that the power factor is unity, which it actually it is, right? So that will give you a number somewhere around 3 kilowatt or so, right? So what that means is that, like with a single phase system, you will tend to use these DC to DC converter for stage 2 and these rectifiers for stage 1. And at a higher power rating, like a three phase like DC fast charger, you will use these as your stage 1 and these as your stage 2. So I will again pause here and ask you if there are any questions. I can take it up, or otherwise I'll just go forward. Any questions so far? Okay. So if there are no further questions, so I can just go forward. So now, see, from a charging point of view, that this is a source, the charger is a source, the electric vehicle is a load. Okay. So therefore, the source has to be current source, voltage source, or it has to be and the battery is a battery. There's no. So what happens is that whenever you plug this plug point to the electric vehicle, the first thing that happens is that the electric vehicle will be providing the EV charger with certain information. What information it will provide? It will provide what is my battery voltage, what is my battery SOC, okay, and what is the thermal rating, and what is the maximum current at which I can charge. All those information from the battery management system in the electric vehicle will first be transmitted to the charger. Okay, so once this transmission has happened and it has been acknowledged by the charger, then only the charging process will start. Because otherwise what will happen is that if that doesn't, like the charger doesn't have those information, it will try to plug in a lot of current into the battery. It doesn't know how much the battery can take, so that may damage the electric vehicle. So therefore, the first thing will happen, what will happen when a charging plug is connected to the electric vehicle, is that certain information are shared between them. All right. So with that, like I told you, that when the battery SOC is very high, okay, then the EV charger will become like a voltage source. Okay, and when the battery SOC is kind of low, the EV battery SOC is low, it will convert it to a current source, because we need to do CCCV charging. Okay, so that is what actually happens. So now, uh, like I told you, that there is a communication that happens between the battery management system and the charger before any power exchange actually takes place. So what is that communication? So for that, if you look at the plug point, there are three pins that are given for communication. One is CP, PE, and PP. So this is one is a proximity sensor, one is a control pin, and another is a protective earth pin, right? Protective earth pin. So so these are the pins that are actually required for the information from the battery management system to be transferred to the electric to the charger itself, right? So that it can. So let me see if I have some slides for you or not. So the first one is the protective earth. Okay, so let's talk about these pins. Okay, this pins here. So let's say we have a protective earth. So this is, by the way, the CCS2 charger. So combined charging system. So combined charging means it has AC charger as well as DC charger. So AC charger will have a line and a neutral. Then these communication pins are common, and for DC charger there is a DC plus and DC minus, and communication pin will again be common, right? So the first communication pin is the protective earth. So what it is basically doing is that through the protective earth, the vehicle, electric vehicle, will actually be first earthed. Like the earthing of the electric vehicle has to happen. So that, because see, you can think now the vehicle is running on four wheels. So these tires are rubber tires. They are not like they are electrically insulated. So first thing that the electric vehicle wants to do is that there has to be a protective earth. That means the vehicle is actually like fully discharged, like it's earthed properly. The chassis is properly earthed, so that it is for our protection. It is very important. So this is the first thing that will kind of happen. So now the second thing is proximity sensor. The proximity sensor, that is PE pin, right? So this pin here, proximity PP pin, connection pin. So proximity sensor pin, it actually is basically required to know whether the plug point is properly connected to the charging plug or not. So the plug point, if it is properly connected to the charging point, then only it is called a proximity sensor, right? So this is a very important pin, because what it shows is that that like unless the proximity pin is properly connected, then what will happen is that there will be a high resistance between the plug and the charge and the EV battery, right? So if there is a high resistance and you transfer a lot of current through it, then there will be I square R loss. So that will create fire. So that is why this proximity sensor will be very important for us. So then there will be a control pin. So the control pin, what it is doing is that it is actually like this is like if it is a DC charger, the control pin behaves differently. It is a fast charger, the control pin will behave differently. And like there is something called a CAN bus communication. So it will provide a duty cycle. If it is less than 5%, then the electric vehicle knows that a DC charger is connected to it. If the duty cycle is more than 10%, the electric vehicle knows that it is a AC charger connected to it. And depending on that, there will be the BMS will provide information to the charger to supply current, right? So this is one example of a charger. Like the primary stage is a PWM rectifier, and then there is a DC to DC converter. This is a very common fast charger that we have. So it is a LLC resonant converter for the second stage, and a PWM rectifier for the first stage. I'm not going into power electronics, because that will actually bore you a lot, because that involves a lot of operation of the converter. So we were looking at things from a more holistic point of view, right? So this is how a charger power stage will look like. Then there will be a control stage, and you can see that the earthing on the primary side and the secondary side are different because of the galvanic isolation. So anyone who is standing here and touching the secondary side is actually electrically insulated from the grid, so that they don't actually have like they don't have shock, right? So is there any questions so far? All right. So now think about like we have talked enough about charger. Now let's see what happens to the charger when it is connected to the grid. So let's say we have a uh, um, uh, we have a 3.3 kilowatt charger, like a normal onboard charger. So let's say there are 100 vehicles in your apartment complex. So that means if they all uh, charge the vehicle at night, then extra power that will be required by your apartment complex will be 330 kilowatt. Okay, and there are 1,000 vehicles, it will be 3.3 megawatt, and if there are 10,000 vehicles, it's 3.3, sorry, 33 megawatt. So you can see that there is a periodic rise in the amount of power requirement just to charge electric vehicles, even though they are using a 3.3 kilowatt charger. Okay, so in India, like previous like 2 3 years back, 30 lakh cars were sold. Right. So from that, let's say 10% of that are EV, like 3 lakh, and like 80% of them, let's say, charge. Right. So there will be extra power requirement of 800 megawatt. Okay. So this is a huge number that has to be kind of supported. So just saying that everyone becomes EV is not a very prudent thing to do, because until and unless our electric grid can take care of this kind of load, and this is very unpredictable. Some people will charge, some people will not charge. So it's a very unpredictable thing. So therefore, the electric grid has to kind of be prepared for this kind of scenario before we can even think of all EV kind of thing, right? So that is where the charging infrastructure kind of comes into picture. So because of this unpredictability, okay, and think about a charger, like if I have a fast charger, let's say this is a fast charger, I charge it at, let's say, 800 kilowatt. Okay, let's say I have a 800 kilowatt fast charger. Okay, and then 800 kilowatt is instantly kind of demanded from the grid, and for a very short time, and after that it just subsides. So therefore the grid has to be now designed for 800 kilowatt more, right? So therefore, in order to take care of that, normally energy storage is being put. Actually, normally the demand of high power actually comes from the storage, so that it has less a burden for the grid. So it actually, demand for high power will be coming from the storage and charging the vehicle, so that the storage discharges, and the grid will be slowly charging the storage whenever there is a lean period, right? So that is how the charging infrastructure is actually made, right? So these are the control layers of a electric vehicle. So the primary control means the switching scenario, and then the secondary control is basically when you have, let's say, many vehicles that are there, how much power each vehicle will take. Okay, that will is taken care by the secondary control. So think about a EV charging infrastructure where there are two chargers. So now in the two, like both are, let's say, 30 kilowatt charger. So all of a sudden, some one vehicle comes and plugs into the first charger. There is another vehicle who comes and plugs to the secondary charger. Now two vehicles are there. 60 kilowatt is the total rating, and let's say 60 kilowatt is the transformer rating as well. So how much power will be taken by each one of them will be actually decided from the by the secondary control now, right? Because one vehicle may be almost fully charged, taking less power. Another vehicle might be uh, not so fully charged, it is having low SOC, and it is taking 30 kilowatt. So one may be taking 30, another may be taking 10. But this division of power, how much they are taken care by the secondary control, so that all the protections are kind of properly operated. And then when you go to EV charging, you can see that there are cameras that are there, or there is a RFID which you kind of put, or you have your like credit card which you actually put. So all those things, like credit card, when you put a credit card, the charger recognizes you. Then because it recognizes you, because it actually transfers the information of the credit card through internet to some server. So that means there is a tertiary control that is basically required. So all these controls have different speed. Like primary control, the switching frequency of a converter is hundreds of kilohertz. Secondary control, it may be in hundreds of hertz, but tertiary control may be in seconds, because the of information from the vehicle, from the charger to the central server, maybe in seconds, right? So therefore different speed of chargers are basically required here, right? So uh, now, whenever we think of a EV charger, like if you talk to your family members, so one of the thing that will be asked to you is that, like what is the, like from a customer point of view, what is important? Charging time, whether chargers are available in my area or not, what is the cost of charging, okay, and if my vehicle goes bad, whether it can someone can repair it or not, and more importantly in India, if I sell my vehicle, how much resale value will get, right? uh, so these are the information that have to be first sought out before EV can become very popular. Okay, if you cannot sort out this information, then it will not become popular. So similarly for policymakers, what is important, that so many electric vehicles are used, so many batteries are used. So all those batteries, when they go bad, they will be dumped into someone, and this battery is a chemical. It's not a uh, like a metal or mineral, right? It is a chemical thing, right? So therefore it just cannot be abandoned like that. It, like, is there a way to make second life from that battery, or where do you source this lithium, if you have lithium, and then how do I skill the manpower so that they can take care of the charger as well as the EV when they go back. So from a policy maker and a student perspective, these are the important things that we will kind of see. So now one of the things, so far, is there any question? I can take it up. I might be going a little bit fast, but if there are any questions, I can make it up. Okay. All right. So now the one of the questions that I have seen, and that is why I've included a few slides on that, is like, as a academician, should we go for commercialization of the thing, like startups and things like that, or we should do publication? We used to do publication a lot. So should we continue on that route, or should we go for commercialization? So if you go to project review meeting, this answer will be very clear. Okay, so nowadays, India aspires to be self-sufficient. We want things to be designed here so that we can give job to 10 more people. So that is a very important criteria for the policymakers as well as for the Indian engineers right now. So therefore, it has become very important now to commercialize stuff rather than do just simple publication and things like that. So the importance of publication over the next 10-15 years will actually kind of reduce. The reason is that we want to make it ourselves, right? We were like, if you like, one of the examples that I give is that if I ask any one of you to give me 10 rupees, you will not give me, okay, or you will be giving me with a lot of heartache, right? But for 3 years we work um, day in and day out, and after 3 years, when we have the result, we actually write a very nice paper and give the copyright to IEEE. So without any hesitation we do that. But if I ask you 10 rupees, you will not give, right? So this mentality has to change, that we actually have to indigenize thing and do work for the betterment of our country rather than just publishing something. Publishing as such is not bad. What is bad is that thinking that publication is everything is the problem, right? So that is where the this commercialization versus publication things come into picture, and government is also putting a lot of effort into commercialization. So from an industry scenario, you can at max go to a prototype demo or initial productization of from the industry. Like, this is at best you can go. This packaging and compliance, unless and until it is done in because it has to be done in specific labs, so that cannot be done by university. Like, the certification authority is not the university. It has to be in India, it is ARAI or ICAT. They will be doing this EMI compliance testing. But okay, at a university level, maximum people can do a lab level demo or a validation under operating. Like the number of like success stories will reduce as we go up. Actually, more people can do lab demo, and very less people can do prototype demo. Things like that, right? That's it. So now the question that I always ask is that how do you know what to commercialize? Like in a EV charger, what should I commercialize? Should I actually make a charger and commercialize, or can I just make a small component of a charger and commercialize it? Or can I do a software and commercialize? So this actually comes from your PhD, like wherever you are trained the best, or any when I say PhD, I mean the experience that you had. So if you are actually trained in electrical engineering, don't try to do computer science, because you will not be successful. Okay, if wherever you have spent a lot of time developing and gaining your knowledge, so use that. So that is actually coming from ikigai. So uh, whatever you are good at, just stick to that. Then you have more chances of success in that one. Okay, and then always understand that you are not the first person doing it. If something money can be made of something, Westerners will sell it to us. It's not like they don't need you, okay, or me. Okay, they know what they are doing. But whenever they're not doing something, there is a reason why they are not doing it. So what is that reason? That if you understand, then you will understand why certain product, like it's like wireless charger. So many in India work on wireless charger. So if wireless charger is that important, Americans will sell it to us. You know, it's a one-day job for them. But why are they not doing it? So that is something Indians have to understand. It's just saying that I know wireless charger and it will sell. Okay, you don't feel bad about it, but that is like we have to retrospect and see whether something is of importance, and if it is important, why are the Westerners not doing it for us, right? Or like they are doing the charger, why are they not doing the like wireless charger for us? So if we have a proper reason for doing it, then only do it. Otherwise, don't do. Okay, and it is like there is a lot of failure that will happen. So be prepared for that, and because when you do product, a lot of failure happen. So always be honest with your industry partner and do that. Okay. And whenever you do a industry commercialization, there are many aspects you have to look at. Okay, NDA has to be done. A lot of different aspects. It's not just making a lab prototype and selling it. It's not like that. There are more deliverables than a lab prototype, right? So these are some of the commercialization that we have done over the last few years. With American Battery System, we made a converter, like the whole converter for them, a DC to DC converter for them at 1800 volt input and 24 volt output. It's a published work. You can have a look at it. Similarly, even a component can be commercialized. For Minda Corporation, we actually made a small residual current sensor for them. So that also we kind of transferred the technology to them. And then you can also transfer just a firmware, right? Like microcontroller programming, that also can also be commercialized. So GE came to us and asked for a program, for their wind turbine. So they asked us, and we kind of did it for them. So that was another kind of success story there, right? So if you see what has happened over the last few years, is that me or people like me have moved away from publication towards products and patents. The reason being that with our current Indian scenario, publication doesn't make much sense anymore, because until and unless we give employment to our general public, uh, our research has no meaning actually. We are not here to we are not a outpost of Americans to do research and give it to them. No, we are actually not. and they don't give any value to us as well, right? You can like from a technology point of view, I think we are rated far below many other people. It will sound bad to you, but that is what it is. That is what the reality is, right? So so the best way to gain our confidence and our and be more beneficial to our system is to do more product, and that those products has to be patented. So I have seen that there are a lot of patents that are being published from universities, but the patent has to transform into product. Only doing patent is also not good, right? Because you are just unnecessarily doing some patent which has no value, right? So the patent has to transform into product. That is what we have to look at, because once it transform into a product, then a commercial partner can take that product and commercialize it, and that will give employment to 10 more people. So that is the idea here. So with that, I will actually end my talk, and I'm requesting that you can ask like any questions that you may have. Any questions?
No. Yes, sir. There are some questions from the participants.
Yes, please, sir.
There is a participant, Mrigunka Mukherjee. And he has asked that what about battery cost, replacement cost? Regarding this, how many cycle can be used in a battery?
How many cycles? Cycles are like this, like battery type of question. I will not be a good person to
Okay.
answer. But cycles, like for 3 years, it doesn't have any problem, right? Like our cell phone, right? That is the point. Like for 3 years, we actually do not have a problem. But what is the first question? I forgot the.
She's asking that what about battery cost or replacement cost if we
Oh,
consider cycles?
but replacement cost, like that is a manufacturer thing, right? So normally what they do is that they like Nissan or companies like Nissan, what they do is that they take small amount of money every month, and every like few years they replace the battery. Okay, so like battery and how battery perform is related to the person who is selling you the car. Not the person, the company who is their policy will actually decide. But normally what they do is that 3 to 4 years you go to their station and they will replace the whole battery, because they don't want battery swapping and things like that. See, people in India work on battery swapping, this that. No, that will not work, because the problem with India is that people will put low quality battery into your vehicle. Okay, so that you understand what that means, right? So therefore the companies are very serious about batteries. Okay, and they will say that every 3 to 4 years you come to our station, and there we will replace your battery, and that will be like if you are paying every month, then that is included in your cost. If you are not paying any month, then you can pay a lump sum, and that can be done. But I actually am not the right person to answer about battery. I know that there will be a lot of questions about batteries, but I'm not actually an expert in battery. I'm more into charger and charging infrastructure, because I also saw one question about some sulfur battery or something. See, I'm not the right person to answer that question.
Another question from Mr. Narendra. How do we decide the capacity of charging station versus filling station?
Capacity of charging station. Okay, so mostly now all the charging like stations, they are fast chargers, because like I told you that they are like they are on the highway, right? So whenever you are going to a charger, okay, so it has to be a fast charger, because you are on the highway, so you have to basically charge your vehicle fast and then get out from there, get to your home or whatever destination you are going, right? So therefore these chargers are generally fast chargers. Now the question is that what is the capacity of that fast charger? That is the question, right? So normally the capacity is 30 kilowatt multiple, right? So it can be either 30, 60, 90, something like that. So now, like generally, what happens in India is that they will provide multiple 30 kilowatt charger. The reason is that then they can process many vehicles. Okay. So, and the problem is that in India, na, the distribution transformer, like if you are going through Prime Minister Yojana, there is something called Prime Minister Electrification Yojana. So there they will give 60 kVA or 100 kVA transformer to you for free, right? So that people kind of try to use, because then 100 kVA transformer, that cost you don't have to worry about, the government takes care of it. But once you have got a 100 kVA transformer, you can only have 330 kilowatt charger, right? 90 kilowatt kind of a thing, right? So that becomes your limit. So like you can have a very high capacity 90 kilowatt one charger or 330 kilowatt charger. In an Indian scenario, having 330 kilowatt charger makes more sense. Okay, the reason being that if the vehicle numbers are high, na, so then it makes more sense. And even though let's say one charger becomes bad, at least two more are available to you. So that is how the decision making actually happens. But that is again very much dependent on who is installing it. Right? But these are the thoughts that people will generally give when they like make this charging infrastructure. Any other question?
Another question is that is there any charging facility for different voltage leveled vehicles?
Come again? I didn't understand.
Sir, he has written charging facility for different voltage leveled vehicle.
No. Charging. See, normally it is about the rating of the battery. So if you are doing slow charging, it will be a AC charger, and the maximum capacity is 7.2 kilowatt. And if you are doing DC charging, it will be a fast charger with a minimum of, let's say, 25 to 30 kilowatt. Okay, and it can be 50 kilowatt as well, 50, 60, 90. That is also possible. Normally in India, people will put either a 25 kilowatt or a 60 kilo, 50 or 60 kilowatt. That is something that is very common in India. But it is not to do with the voltage, it is to do with the charging. Like slow charging, 7.2 kilowatt, single phase. Fast charging, 25 to 50 kilowatt, three phase. It's not dependent on the battery. Battery voltages are both in same because they are charging the same battery, right? There are some elaborate on sulfur. Sulfur battery, Sureshji, I don't have much understanding of battery, so I cannot comment on that. To charge a battery, how much capacity is needed approximately? Uh, 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 Capacity can be 50 kilowatt. If it is a 30 kilowatt hour battery and I'm charging at 60 kilowatt, then it will take half an hour. So charging capacity will reduce the charging time. So that is the whole game here. So there is no minimum or maximum capacity. Like because it's a lithium ion battery, I can charge at 2C, 3C, etc. Right? So I can reduce the time. So that is the answer. Ankit Ji is asking, sometimes it is written as level 1, level 2, level 3 charger. Level 1 charger like 1 kilowatt, level 2 like 3 kilowatt, level 3. So this is a wattage rating. That is precisely what they are saying. That is for the, see, level 1, level 2, level 3 for AC charger also is there. Level 1, level 2, level 3 for DC charger is there. See, I wrote a paper on chargers in 2017. Okay, it is actually in IEEE. So now when I read that paper, it is extremely outdated. The reason is that at that time, whatever was there, I wrote that. But with time, what has happened is that AC and DC fast charging, this AC charging and DC charging, both have their level 1, level 2, level 3. Okay, these are all like terminologies people come up with to basically woo people. There is no like another 10 years these things might change. Okay, so basically level 1 means low power, level 2 is little bit high power, level 3 is more high power. So for a AC charger also this is there, for a DC charger also it is there. Alright. So these numbers are just charger rating that they're talking about, and you can get it from the internet that what that charger rating is. I think level 1 is about 2 kilowatt or so, and level 2 is little bit higher than that. Level 3 I don't remember the numbers, but yeah, these are to do with the ratings, right? Suresh is asking, in a AC and DC grid, how loads are shared among DERs. DER will be different rating. What sources? So, see, normally, I think you are asking more a question on microgrid. Okay. So, normally, what happens is that when you are having two different two different sources in a microgrid, normally they do a frequency control. If it is AC, okay, in AC they will do a frequency, power versus frequency. They will have, they will change the frequency to control the power. Okay. But in a DC, they will actually go for a droop control. Droop control means they will actually change the voltage and do the power control. See, ultimately, think about a DC. Right? It's like the load is voltage is constant because it's connected to the same grid. So it is V. Okay. So now, if I control the voltage output of source 1 to V1, then the power transferred will be V1 minus V divided by the resistance between them. The second source, if I control to V2, then it will be V2 minus V divided by R. So this, by controlling the output voltage, okay, I can actually control the power that is transferred from the source to the grid. So for a AC system, frequency is basically changed to control the, or to share the power, and in a DC system, voltage is basically changed to share the power. Hopefully, Sureshji, I answered your question. Okay, and no more question. Any other question that you have? Any other questions? Okay, so I am done. Manmohan, if you are around, I am done.
Sir, he is taking class in the.
Okay, all right. So if there are no further question, can I log off?
As you wish. Thank you.
Okay, all right. Thank you.